All right, let's talk about inverse functions. And the math definition of an inverse function is not helpful. But, okay, so conceptually what's happening is these functions are going to undo one another. And so why that happens, so we should think of functions as verbs. And so, for example, if we look at this line, so if I have a number x and I perform f, then in this first example, f is the action add 1, right? And f doesn't care if I feed it a number or if I feed it some other more fancy expression. Okay, it just adds 1. That's what f does. It's like some mindless assembly line member. It's a robot that just adds 1, and it doesn't care what you feed it, right? So how do I undo that? Well, I should subtract 1. So if I subtract 1 to what's given to me, then, plus 1 minus 1, you get back to where you started. So what I wrote here is analogous to this expression. I did f, and then I did f inverse. And what I started with is what I ended with. I started with x, I ended with x. Start with 7, you end with 7, if you do this kind of thing, right? So, okay. And we use this type of symbol to denote the inverse. I know it kind of sucks because we're used to, I say used to, but typically if we're dealing with numbers, then this symbol is refers to bringing something onto the denominator, or reciprocal, which is an inverse for multiplication. So like it kind of makes sense in this type of setting. Sorry, my dog is such a loud drinker. Okay, so, and we can see this again. Let's just run through really quick. So if I have x and I perform f, and so here's my f, then I get 2x. And if I perform f inverse, then that means I have to multiply what I fed it by a half, and I get back to x, right? So, okay, and it doesn't matter who goes first and who goes second, right? If I first multiply by half and then multiply by 2, so I first multiply by half and then multiply by 2, indeed, x will still be x. Okay, so conceptually, inverse functions undo one another, and in order to undo a function, you sort of have to go in opposite PEMDAS order. So when you compute a function, you go in this direction with PEMDAS. For example, if this was my function, x cubed plus 14, and I was curious, what's f of 3? Well, first I would cube 3, and then I would add 14, right? This is very different than if I first add 14 and then cube it. Those things are not the same. They're so far apart. Okay, so there's sort of that order. Now, if you're going to invert something, if you're going to undo something, or if you're going to solve for, we'll see how these are related in just a moment, you go the other way. So this is something called the shoes and socks lemma in mathematics. So when I get dressed, I put my socks on, and then I put my shoes on. I first put on my socks, and then I put on my shoes. And when I get undressed, getting ready for bed, I first take off my shoes, and then I take off my socks. You have to do the opposite thing in the opposite order, and we see that happen in math as well. So if I first cube x, and then I add 14, when I undo everything, I have to first subtract the 14, and then cube root the result. So we can compute this object here. So we're performing f on this more complex expression. So what does f of something do? Well, it cubes that something, and then it adds 14. I'm looking at this function here. Okay, and that something does not have to be x. Okay, we use x as a dummy variable to demonstrate what the function is doing, but the function is the action. And what's the action? It's cubing and then adding 14. So in here, I'm going to put f inverse, and what is f inverse? It's this. So I'm going to put the cube root of x minus 14. And now a cube and a cube root cancel. And so what I get is just, well, I guess I'll write it like this, x minus 14. The cube root's gone, it cancels with the cube root, plus a 14. And hey, look at that, those cancel, and now I just have x. Okay, so indeed, we see this type of phenomena happening. And so you can see that this is the inverse of that. But also we see it in words, right? It's doing the opposite stuff in the opposite order. Okay, so we'll come back to exercise 4 in a moment. I just want to talk about the inversion algorithm. So here we're looking at the equation form of a function, okay? There's an equal sign. This is an equation because it has an equal sign. And if I was to graph, say, this curve, then I pick an x value, maybe 1, and the way I find the y value is to perform the function, right? This is why we write y equals f of x. So 1 cubed is 1, and then plus 14 is 15, so 1 comma 15, also known as 1 comma f of 1, okay? And this might feel a little uncomfortable to write it like 1 comma f of 1, but in fact, every graph you've ever seen is x comma f of x. This is why people write y equals f of x. They're saying, hey, that y value, it's equal to f of x. This has been going on behind the scenes all along, okay? So anyway, the way, when I wrote this, I originally just wanted you to solve for x, okay? So if we do that, if we just solve for x, then I need to get this thing by itself. And now I'm going to go back to my PIMDOS comment. If you're solving for something, then you go in opposite order. So I'd look at this and I would ask myself, is there addition or subtraction? Ah, yes, there is. Let's get rid of that. And by get rid of, I mean like, is there addition or subtraction happening on the side with the variable I care about? And if I care about x, then it's happening on the right-hand side. So I'm going to move over that 14. And okay, so now I've done that. Is there multiplication or division? No, there's not. Is there an exponent? Yes, there is. So let's take care of that by cube rooting both sides. And so now I've solved for x. X is equal to the cube root of y minus 14. So as this is written, this is saying x, and I've actually found the inverse function. It's f is inverse function of y. But we don't like to write stuff like this. Okay, so what if you do what I wrote here, then in all of these examples, you would have found the inverse function. It would be a function of y. But again, what you call the input does not matter, right? Notice it's the same here and here. It's the same verb. It's the same action. It's subtract 14, then take the cube root of that, okay? So in order to have the form we want, did I write it? No, I didn't. So the form that you'll often see is this, okay? In order to have that form, I'm going to give you a little algorithm for it, and it begins with swapping x and y, okay? So let's go ahead and swap x and y. So I have x is equal to y cubed plus 14. I literally mean, when I say swap x and y, wherever there used to be an x, make it a y. Wherever used to be y, make it an x, right? So if I do that here, I'd have x equals the square root of 3y minus 2. And if I do that here, I have x is equal to e to the y plus 4, okay? Now, the next step is to solve for y. And notice, solving for y here is going to be the same action as if I solved for x here, right? They both are saying, hey, let's subtract the 14, and then let's cube root the result, right? So we already know where this one's going. This one is sort of beaten to death. Sorry, my cats are being crazy. So we would first move over the 14, and then we would cube root the result. Here, we can go in a couple of steps. So let's square both sides. We have x squared is 3y minus 2. And then if I add the 2 over, I have x squared plus 2 is equal to 3y. And then if I divide the 3, then I'll have y is equal to x squared plus 2 over 3. Okay? And finally, so let's move that 4 over. I have x minus 4 is equal to e to the y. And now, the natural log of whatever, okay, if I put an, I'll say this, if f of x is natural log, no, we'll do this. If f is e to the x, okay, f of x e to the x, its inverse is natural log. Okay, what this is saying is, what I'm trying to tell you is this relationship about natural log. If you perform exponentiation or natural log one after the other, they'll undo each other. So if I use my labeling from below, this is how I labeled it. Okay. So what is this expression saying? It's saying first perform the natural log of x, then make that the power on e. Okay. F inverse x is natural log x. F is, make that the power on e, okay? And that will equal x. These two things will undo each other, you'll get x. Similarly, if I took the natural log of e to the x, I would get x, and that's what this one's saying, right? Natural log is the inverse function of e, so I should apply the natural log to both sides. I have the natural log of x minus 4 is equal to y. So in each of these examples, we found the inverse function to what was listed over here, okay? So if this was named f of x, then this would be named f inverse of x. If this was named g of x, this would be named g inverse of x, and so on, right? And okay, so when you do this swap, and then you solve for y, so when I perform the swap, okay, going from here to here, and then I solve for y, let's see what it looks like on a graph first. We'll come back to this table one, okay? So the whole idea is, so here is the function x cubed, okay? X cubed. And, oh, apparently, sorry, x cubed divided by 2 is that function. So if I were to compute f of 2, I have 2 cubed over 2, better known as 2 squared, or 4. So 2 will map to 4, right? If you plug in 2, and then f of 2 is 4, okay? Now, to swap x and y, you literally just swap who's who, and then that'll give you a graph of the inverse function, okay? Now, what I want to say about all this is, in the beginning, so if I have something like y is x cubed over 2, and up here, when I first, it was this arrow, okay? I was saying solve for x, okay? The idea of solve for x, what that's saying is if you start somewhere, for example, let's start at y equals 2, right? I'd go until I hit my graph, and then I'd figure out what was this x value that got me to y equals 2, right? And what that looks like algebraically is I plug in 2 for y, and I solve for x, right? So, right, this process, if you stare at it long enough, you'll realize, well, wait a second, that's, what am I trying to say here? Remember up here how you could either solve for x, or you could swap who's who and then solve for y. And, really, right, if I swap the name x with the name y, then my old instruction of called solve for x, well, now x becomes y, so this would say solve for y, and that's indeed what it says. Swapping x and y would put this point over here, right? This is something comma 2, and now it's 2 comma something, okay? Maybe I should use the question mark instead of an x value, because, this question mark represents a number, but we're so used to x referring to the number on the left side of the comma that when I put an x here, it might be a little confusing. So if I first swap x and y, that takes this point here to this point here, okay? I'll call this one A and this one B. So it sends A to B, okay? Now, if I solve for y, that's the same as if I had solved for x before swapping. So anyway, the graph of an inverse function, it's just the graph when you perform this swap, okay? It'll naturally just sort of be what it has to be. And we can see that happening. 2, 4 gets sent to 4, 2, and have the inverse function written down here, but we can just do what we know we should do. So I would first swap x and y, so I have x is equal to y cubed over 2, and then I solve for y, so I have 2x is equal to y cubed, and I cube root both sides. I have y is equal to the cube roots of 2x, which is also the 1/3 power of 2x. Okay, and So this idea of swapping who's x and who's y, that's one way to think of what an inversion is. You just swap x and y. It's not the most enlightening on how it all works out algebraically. Okay, so let's go up to this table form, and we can see it happen again. And I just copy and pasted this from the first quiz, but let's just focus on these first two rows. Okay, so, or first two columns, my bad. I'm going to call this y, and I'm going to tell the reader y is equal to f of x. So in other words, f takes you from this number to that number, or this number to that number. Said differently, f of 2 is equal to 3. F takes 2 to 3, right? Said differently, if I were to graph f, it will have the point 2, 3 on its graph, right? If I graph f, then I'll have minus 3, 4, minus 3, 4. I'll have 1, 10, 1, 10. I'll have 2, 3, 2, 3. And I'll have 4, 7. 4, 7. Right? There's my graph of f. I just put down all of these xy pairs. XY pairs, right? Okay, well, if you want to graph f inverse, just like I was saying in the previous thing, so we're going to call this y, this is x, right? F is the relationship where this column is x and this column is y. This column, the first one, is your horizontal, and this column is your vertical, right? But if you switch them, and instead, this is going to be the horizontal, and this is going to be the vertical, okay? Well, then I should go to 4, 3. And so here's 4, negative 3. Negative 3, so maybe I'm here, right? So 4, negative 3. And what this is saying is f inverse of 4 is equal to negative 3. F inverse goes this way. F inverse. It will undo f. It will undo f. So f sent minus 3 to 4. F inverse will undo it. It'll send 4 to minus 3. Okay. So, and in the table form, remember, inverse function is defined mathematically by stuff like this. And in the table form, I claim it's super easy to see, right? So if I have something like, and now, okay, let's think of how to finish this together. I want this expression to make sense. So I need to pick a number that I can plug into f inverse. So let me tell you what a bad number is. Do not put down 1. Okay, that's a bad number because f inverse goes from this column to that column. So is the number 1 in this column anywhere? No, it's not. So I don't know what f inverse of 1 is. I don't know. Okay. Now, if the problem said, hey, you can actually plug whatever number you want into f and f inverse, everything's going to work out fine, then I could say, okay, the answer is 1. Because these two things in succession will undo one another. F will do something like this, f inverse will do something like that, and they just undo one another. Okay. But there's nothing in this problem statement that says f is defined everywhere, or f inverse is defined everywhere. So I cannot assume that I can plug numbers in here that don't appear here. Okay. Oh man, my cats are on. All right, so let's go ahead and finish up exercise 5. Did we do exercise 4? Yes, we did exercise 4. Okay, so swapping for x and y, that's at the core of inverting functions. And in tabular form, solving for x is so much easier, right? Because if I asked you, hey, y equals 4, and I'm referring to the function f, what is x? Oh, you'd say y is 4, x is minus 3, right? Alternatively, if I said this, not minus 4. If I said f of x equals 4, what is x? You'd say minus 3, right? So in tabular form, it's super easy to do that. What points live on the graph of f? So I already sort of answered that when I was previously like graphing f, right? And you have x and y, and you just sort of graph them. If f of x equals 10, what is x? It's 1, because the y value is 10. Okay, make a table for G inverse. All right, so let's make sense of that. And there's one confusing thing here, okay, is that x is what we call the input for G inverse. And the input for G inverse is going to be this column here. And this is understand, like if this is confusing, it's understandable. This x here is different from this x here. Okay? The x highlighted in yellow, okay, this one, it's what we call the input for G inverse. It's a placeholder for a number that you can plug into G inverse. These are the numbers that I can plug into G inverse. Okay? Because G inverse takes something from this column as input and spits out something in this column as output. For G inverse, these headers are wrong. Okay? This column doesn't even matter. Okay? For G inverse, this is y and this is x. And this is y is G inverse of x. Okay? The name x, like, it's context specific. And that can make math very confusing. Okay? But, is there a good analogy with the English language? It would take me a while to think of it. Okay? Yeah, I don't know. I don't know off the top of my head. Sorry. But implicitly, in the table that's given, let me just get rid of this. Okay, in the table that's given, we could call this x and g of x, and that's fine. But I guess really this is like inputs for g, and this is the outputs of g. Okay, and gosh, look at how many words that took. So we just call it x. Okay, and similarly here, this is inputs. I already wrote it and then I erased it. Inputs for G inverse. But you, what did I say? You have to swap x and y. And these should really just, man, everything just goes in quotes here. G inverse of pi makes sense. G inverse of pi is 2. Okay. Whereas G inverse of minus 3 does not make sense. Okay, it's undefined given the information. There is no negative 3 here. Right? And G inverse goes this way. And so whatever you call this, if we call it x, fine, ignore the headers here in the sense that, like, this x and this x are different. Okay? That's the most subtle and confusing point, and I don't think we ever really test you on that very hard, so don't worry too much. Okay, so if I were to make a table for a G inverse, what does it look like? Well, I copy down this column here, so I have 1, 7, pi, 2, whoop, whoop, and that's x. That's what I get to plug in to G inverse. And if I plug in 1, I get minus 3. If I plug in 7, I get 1. If I plug in pi, I get 2. And if I plug in 2, I get 4. This is my table for G inverse, okay? All right, and I hope you can see how it's like swapping x and y, right? I just swapped these two things. All right, so now we go back to the graph stuff. And this is where I want to pause and show you something that maybe it'll blow your mind, maybe not, I don't know. So let's hop over here. And yes, I want Desmos. Great. All right, so here we are. This is f of x is equal to x cubed. And I'm going to swap x and y, okay? Now, even if you don't know why what's about to happen is about to happen, you should pause the video and ask yourself, when I click Desmos to show me this graph, what is it going to look like? And big hint, what's been happening every time I swap x and y? Right? So you get the inverse function. You get the inverse function. And now I don't know how to ask Desmos, like, for example, I can't just type this. Okay, doesn't like it. Maybe out of curiosity, if I did this, nope, it doesn't like it. Okay, but I do know the inverse of cubing. It's the cube root, and the cube root is x to the 1/3. And notice, right, it's the same as that green line or green curve, because, well, if I right here, what this is saying, so Desmos knows the function f. It knows the function f is the cubing function. So 2 cubed is 8. And if I say, hey, what's f of 2? It would say 8. Okay? So what this curve is saying, it's saying x is equal to y cubed. Y cubed. Okay? Now, if you solve for x, then you would have, if you solve for y, you'd have y equals the cube root of x. And that is why they all line up. Okay? So, anyway, let's hop back over here. You can play a little bit with that in Desmos. In fact, let's play a little bit more. I'll just show you one more thing. Desmos is more lenient than a math class. Okay, so here's a function that is not invertible for all x. Okay, what I mean for all x is if I draw the horizontal line, let's say y equals a half, okay, then I intersect at many spots, okay? So what this is saying is if you had to solve the equation 1/2 equals sine of x, oh, sorry, I need to pay attention when I type, equals sine of x, there are infinitely many solutions. This equation is not, it doesn't give you one single x value, okay? Which means if you try and find x given a y, when your function is sine of x, you cannot get a single specified x value. You're going to get infinitely many, okay? And that means it's not a function, because it would fail the, technically it's a vertical line test, in this case the horizontal line test, whatever, we're getting lost in some details, don't worry about it. Nonetheless, this type of question still makes sense. 1/2 equals sine, right? And the definition of a function is sort of like very restrictive mathematically. I can still do the inversion process, right? Here it is, boom. And so notice this black curve, that's not a function. It would fail the vertical line test. So now if I did x equals 1/2, okay, then this vertical line intersects that black curve a lot, okay? But you can always do this reflecting x and y. And so now you might say, but wait a second, I thought the inverse function of sine is arcsine, and that's true, you just have to restrict yourself. So let's see, sine is -1 at minus pi over 2, and it's +1 at pi, oops, put an x here, and then pi over 2, okay. So now, see, these would pass the vertical and horizontal line test. Everything is great, everything is good. And this is the same as y equals arcsine of x, okay. And so notice that black curve got covered up, right? So, okay, so there are many functions which are not invertible in the math sense because the resulting graph, so let me get rid of this again. Okay, this guy, the resulting graph of doing the inversion process would fail the vertical line test. If I get a vertical line, then it'll hit that graph at multiple spots, right? But you can still do this reflection thing. Okay, math can still make sense beyond functions. And this same kind of thing happens if I do x squared, okay? Because x squared fails the horizontal line test, then, okay, and a horizontal line is something like y equals 1, okay? There's a horizontal line. If I switch x and y, then this would become the line x equals 1, because I switched x and y, right? And now, when I switch x and y, that's doing this. And so this black, it's not a parabola, this black curve, it is a parabola in some sense, but whatever. This black curve fails the vertical line test because the blue curve failed the horizontal line test, right? So the blue curve became the black curve. I should make this something else. Let's make it red. There we go. So the blue curve became the black curve when I switch x and y. Similarly, the horizontal line became the vertical line when I switch x and y. So all this is to say, if your original graph intersects a horizontal line more than once, then the inverted graph will intersect a vertical line more than once, which means the inverted graph is not a function, but it is a valid graph. There's some kind of valid relationship between the x and y coordinates. This is subtle. It's not a big deal. Let's go back to this worksheet and finish it out, okay? All right. Oh, yeah, this is what I wanted. Okay, so if you tuned out, if that seemed really weird, let's tune back in. And let's just remember that swapping x and y is sort of at the core of inversion here, okay? So find the coordinates of the two unlabeled points. Okay, so that's these two. And we can see pretty clearly that, like, right here, the y value is 2, okay? So if we go to our function, the y value is 2, and that needs to equal x cubed over 2. And so what do? I multiply the 2 over. I have 4 is equal to x cubed. And so the x value is the cube root of 4. Okay, that's fine. And now when I swap x and y, then that puts the 2 in the x position and the cube root of 4 in the y position. Okay? All right. Find the coordinates of the unlabeled points. Did it. Compute the average rate of change between these 2 points on each curve. Okay? So what that's trying to say, sorry if it's confusing language, is so I go to one curve, here it is, and I want to compute this average rate of change. Okay, so let's do that. I have to do the difference in y values, 4 minus 2, divided by the difference in x values, 2 minus the cube root of 4. There's the average rate of change for this curve, so for f. Okay? Let's do the same thing over here. So now I'm looking at this thing, boop, and I should do a difference in y values. That's 2 minus the cube root of 4 over the difference in x values, 4 minus 2. And I want you to stare at these two things, and how can I go from the a rock on f to the a rock on f inverse? What happened? What happened? It's the reciprocal, right? I just sort of flipped it over. What used to be a over b became b over a. And you know why that happened? It's because this is a change in y, and this is a change in x. And when we do the switch, when we do this reflection here, we're switching y and x. So this y becomes the denominator. It's called x now. And this x becomes the numerator. It's called y now. All right, there's nothing too deep happening here. We switch x and y, which flips over the slope. Okay? And we can see that with lines. Same section of curves, just before and after the reflections, right? How do the two average rates of change compare? They are reciprocals. Why? Because we switch x and y. And so that's exactly going to flip over the slope. All right, let's see it with lines. It's a little bit more clear. So on the graph to the right, graph a line of your choosing. Ooh, all right, line of my choosing. Oh my goodness, I can choose anything I want. We're going to go from, let's say, here down to here. Boom. All right. So let's see. What is this line? This line is y is equal to, well, I have a y-intercept of 2 plus, and what's its slope? I go over 2 and down 1. So down 1, it's rise over run. Down 1 is my change in y. Over 2 is my change in x. So here we go. And if you prefer mx plus b, I should do minus a half x plus 2. Okay, so any of these forms work. All right. So now I'm going to reflect. I'm going to swap x and y. Oh, goodness. Okay, I'm gonna swap x and y. Let's do it for a few points. So, for example, right here is the point 0, 2. That's going to go to the point 2, 0. Right here is the spot 4, 0. That goes to 0, 4. Okay, and this is now going to get really confusing. You know what I should have done? Let's back this all up. Okay, so I'll put in red on the blue line, and then they're reflected spots. So this one is going to go here, and this one is going to go here. Okay. So now, if I switch x and y, it still kind of preserves the shape of the graph in some sense, right? Like this kind of shape, this kind of shape. Like it's this lazy S. Here, a line becomes a line. And so the reason I only did 2 points is because now I can kind of just connect these 2 points And boom, there's my line. Okay. And this line, y is equal to, well, now my y-intercept is 4. What's my slope? Well, now I go down 2 and over 1. So plus, and then what's my slope? I go down 2 over 1, x. So notice, pay attention to the slope. Okay? It's the reciprocal. It's just flipped over. That's all it is. Because what used to be called y is now called x. And so what used to be a change in y divided by a change in x, well, those changes are the same. It's just that who got switched. So that old change in x is now on top, and that old change in y is now on bottom. Okay. All right, play around with that. And this is gonna end up being like not a big deal, but it's one of the things that we're sort of forced to cover eventually when we talk about derivatives. And this picture may be a little bit more intuition, but let me just say where we're going with this eventually in the class. Okay, so if you are standing right here, here we are, okay, and I ask you, what is the slope under your feet? Okay, so the slope on F at, and then what is this? This was that gross spot. Okay, that was the cube root of 4 comma 2 at this spot. Okay. Well, how does that compare to standing here? Now what's the slope under your feet? Okay, so there's a name for the slope of f at this point, and the name for this is f prime at, and then I just record the x value, the cube root of 4. Boom. Okay, so this weird expression here, we'll eventually make sense of it in the class, but it refers to standing right here and answering the question, what is the slope under your feet? Okay. Now, if we're standing right here and ask the same question, what is the slope on, and now this is f inverse, right? It's the flipped over graph at, and now we have the flipped over point. 3 root, boom. Okay, so this, this is where things really suck notationally, okay? So the name of the function is f inverse, and then we could put a prime to mean slope. Okay, this little symbol here is going to refer to slope. So this little symbol is referring to slope. And then what's in here is saying what curve you're on this curve, okay? And then I have to feed this an x value, okay? So I feed this the x value of where I'm standing. I feed this the x value of where I'm standing, okay? So we're going to see this notation a lot later on in the class, mostly this type of notation. And notice, how do the two slopes compare? Well, they are reciprocals. They're reciprocals. And so because this is really gross to write, okay, so we have f inverse slope at 2. What we end up doing is we'll say, well, that's the same as 1 over the slope on f at, and now it's not 2, it's the y value, right? Because these things get switched, right? So at 3 root 4, okay? And this is like, it's, you know, something that'll be on an equation sheet later on in your future, and like maybe there'll be one test question on it. We like to make a big deal of it in calculus, but yeah, whatever. So this is not in your immediate future. I'm just kind of foreshadowing where we're going and trying to give you some intuition on like why these weird formulas happen, right? It's because we switch x and y, so we switch the rise and the run. We just do a 1 over, okay? All right, so what are the key takeaways that I want us to get? So an exponential function means something of this form, okay? And, you know, these are saying the same thing. We just use this little algebra trick that E is the same thing as, sorry, not E, B as in boy, is the same thing as E as in echo to the natural log of B. Okay, so that's an exponential function. Exponentials are the only functions which satisfy this relationship, okay? They're the only function where your next y value, right? We sort of have to get used to this notation. It's kind of weird our first time seeing it, and the more you interact with it, the more it makes sense, okay? So t plus 1 is like you shift over an x, but then saying p of t plus 1 is saying, now what's that y value? So what's the next y value? Well, it's some scaled version of your current y value, okay? Exponential functions are the only functions that do that, all right? They're the only ones. And you can sort of like say this property in two ways. You can either talk about the jump between y values, or you can talk about the y value itself. Okay, whatever. All right, fine. So this is sort of the group of what you should know about exponentials. And then, okay, inverse functions undo one another. All right, so that's what this is trying to say. And this is always a matter of swapping x and y. Okay, understanding how these two things are the same, like we'd have to like think about it for a while and really work it out. But if you sort of know how to find an inverse, then you sort of know what they do. That's plenty. Okay. Now, a very special inverse function are logs. Logs are the inverse of exponentials. So this type of statement is the same thing as this kind of statement. These two functions are inverses. These two functions are inverses. All right. So there's all that stuff. And we mainly use logs to solve for an exponent. Okay. So great, and this will be mainly for exponential growth and decay, and that's because it's super common in biology and chemistry. We want you guys to get some practice with it. Also, just for some intuition on logs, logs grow very, very, very slowly. Okay, to increase an output by 1, output, you should think y value, okay, to go up by 1 unit, x needs to have a b-fold increase, and this is b here, it's the base of the log. So if your log base 10 of 1,000 is 3. Okay, there's a couple ways to see that. So 1,000 is 10 cubed. And remember, log is saying what power on this number equals this number. What power on 10 equals 1,000? The answer is 3. Okay. Another thing we could have done is just divide 1,000 by 10. We'll get 100. Then divide that by 10. We'll get 10. Then divide that by 10, we get 1. So now we can stop, and we ask ourselves, how many times do we divide by 10? 1, 2, 3, okay? So log base 10 of 1,000 is 3. Meanwhile, log base 10 of something is 4. Well, what's going to go here is 10 to the 4th, which is 10,000. So you see, the input, the x value, had to have a 10-fold increase, a b-fold increase, and my b is 10. But the y value, how much did I go vertically? I went up by 1 unit. So to increase the output by 1, x needs to have a b-fold increase, okay? Logs grow very slowly, very slowly. All right, now let's put all of this together into a graph where we sort of want to extract some of the key features of all of this, okay? So let's graph e to the x and natural log x. Oh gosh, how do you graph that, Anthony? Right, so there's a few things we're going to look at. Okay, so one of the graphs goes through 0, 1, and the other through 1, 0. And we should just sort of think about what happens. So e to the 0 is equal to 1. That's an x value. That's a y value. So 0, 1, that is going to be on e to the x. And because this is true, we can write this in log form. And in log form, so this is saying e to what power equals blank. Okay, so e to what power. So the what power goes here, and e equals blank goes here. Okay, so we know e to the 0 power, e to the 0 power equals 1. Okay. Said differently, switch x and y. ln x equals y, but this x is the old y, and this y is the old x, because you want to switch them. So my old x was 0, so now that's a 0, and my old y was 1, so now that's a 1. Okay, so 1, 0. So this is going to be the natural log of x. Okay. Now, I should have extended this graph to sort of have more negative numbers. You can play the same game here, and at 1 we should be at e, which is around here. So the exponential graph looks kind of like this. It just gets really big really quick, and it's always positive, okay? The natural log graph looks like this, and boom, okay? So it's going to grow really slowly, right? It really kind of levels out pretty quickly. And yeah, I really should have extended this picture. Sorry about that. Okay, so the exponential graph has a horizontal asymptote, whatever. We never cross the x-axis, okay? So these two things are saying the same thing. So we never cross the x-axis. Well, if you switch x and y, then that's saying the log graph never crosses the y-axis, right? Okay. So that's this bullet, and then these two bullets are sort of how I drew the curves. So E is about 2.7. So e to the 1, I'm looking for about 2.7. So when x is 1, I go to about 2.7. That's how I got that dot. Whereas the natural log of e is equal to 1. Okay, so when x is about 2.7, I should be at about 1. So I was kind of shooting for around here somewhere. That's that. And then slow growth is swapped with fast growth, right? So the exponential grows really fast, and then when you swap x and y, that means x grows really fast, okay, but y doesn't. Okay, so I like having this picture in mind because this picture, it sort of makes it easier for me to remember that the natural log of 1 is 0. Because I just remember, this curve, okay? And this curve is going to hit at 1, 0. So it helps me remember that about natural log. It also helps me remember that, like, as I walk along natural log, it kind of gets easier and easier as I walk. It really mellows out, okay? That's something we'll see later on in this class. Okay, so, oh, right. Okay, so I sort of don't want to do this last page. This last page is from the sample 1 midterm, but it's showing you relevant material. Okay, I'll run through it sort of quickly. So the mass of an object is modeled by this equation. Is the mass increasing or decreasing? Well, remember, if you have e to the kt, then if k is positive, you're increasing, and that's what we have here, okay? The coefficient out front doesn't matter, okay, because the 10 doesn't change. This is what changes. The 10 doesn't change. This is what changes, okay? Find the doubling time or half-life. Okay, so you would say, when does the stuff that change equal to e to the 0.25t? And take the natural log of both sides. You'll get natural log of 2 is 2.5t. Divide by 0.25. That's the same as multiplying by 4. So I'm going to write it like this. 4 ln 2 is equal to t. Great. You must show the equation you are using. Oh, man, this is such a big deal. I remember there was something like this last semester. And if you don't write down something like that to show where you start, if you just jump straight to here, it's not going to get you full credit. This is why we got to read the question, okay? All right, determine this value. Oh, gross. All right, so this is where, so the answer, okay, is going to be this, all right? You can just do the computation. Algebra makes it a bit easier. And if you're in Jeff's section, then he sort of runs through this to show you that, you get that type of answer. So I'll run through that now, I guess, in the general case. The general case is this for an exponential. Okay, p of t is equal to that. So if I look at the numerator, then I have to do p of 3 minus p of 2 all over 3 minus 2. That is the numerator. Okay. Now if I do the denominator, I have p of 2 minus p of 1 all over 2 minus 1. Okay, now first observation. 3 minus 2, that's just 1. 2 minus 1, that's just 1. What this really says is p of 3 minus p of 2 over p of 2 minus p of 1. Okay, fine. And now if we plug in what that means, right? We have c b cubed minus c b squared all over c b squared minus c b. You might say, oh goodness, how can I? Well, look, anytime you have something complicated, you should ask yourself, can I kind of pull stuff out? Can I simplify the expression? Yeah, up top, you can pull out cb squared, right? So the c is gone, gone. B squared is gone, you're gone, this 3 becomes a 1. Right, b minus 1 over. And on bottom, I can pull out a cb, right? Pull that out, so you're gone, I have b minus 1. And notice, b minus 1's cancel, the c's cancel, that cancels that. All that you get left is b. That's it, just b. Just this number here. And in our problem, we have e to the 0.25t, which is the same as e to the 0.25 to the t. That is b, okay? So that's one way you could see it. I could also connect this back to the very beginning of this because the average rate of change. Here we go. This is the average rate of change from t to t plus 1. Right? Sort of the difference in y values and the difference of x values is 1. And so notice you get this, right? So in our case, we had like a rock 3, 2 over a rock 2, 1. So 3 is playing the role of t plus 1, so t must be 2. So we have b minus 1, p at 2 over, and then this would be b minus 1, p at 1. And you instantly see those cancel, and now the question just simplifies to, hey, what's p at 2 divided by p at 1? And every time I've written p, the question actually called it m, but like whatever. And so now this is much easier. This is e to the 0.25 times 2 divided by e to the 0.25 times 1. And, well, look, you can kind of see, like, this cancels that square. You get this. Okay. So, anyway, all right, that's all I have to say. See you next time.